Hi everyone, hope you're having a wonderful day so far. Today we're going to start chapter 6 and we're going to start about the history of the periodic table. So in chapter 6 we're going to look at an overview of how this periodic table is arranged and how we got there, and then we are going to talk about different trends and different trends and properties that we can see on the periodic table. So by the end of this chapter you are going to be amazed by the periodic table and how it's arranged and how you can look at two different elements, and based on their placement on the periodic table you can tell which one has a higher melting point, which one is more reactive, which one has a bigger radius, and so on. So we're going to start with the history of the periodic table and how it came about to look like the way it does right now. There are hundreds and hundreds of chemists who have been working very hard on this. And we're only going to highlight a few of them, but just know that there are a lot of people that had worked on this in order to get our current periodic table. The first one that we're going to mention is W Reiner. He was a German chemist, and this was in about 1829 when he did this work. You do not need to remember the nationalities. You also do not need to remember the dates or anything like that. This is just for your own knowledge, just so you can, have a timetable for yourself. So what he did was he arranged the elements in triads. Into triads. And a triad means a group of three. So, for example, he put chlorine, bromine, and iodine together. And, sometimes that was for a good reason. For example, he said that they have similar properties. So that was a pretty good reason to put them together. Sometimes, his reasons weren't that great. For example, he said, well, if you take the average atomic mass of chlorine and iodine and add them together, that's going to equal to the average atomic mass of bromine. That really has nothing to do with anything, but he thought it was a good reason at the time. But again, the idea is he arranged these elements into triads. Can any of you think of a problem with that? Well, back then we only had a few elements, so we didn't have as many as we do today on the periodic table. We have 118. Back at his time, they only had maybe 20 some or so. But the problem is that not everything fit. So, those three fit together, but there were some that, he couldn't really fit into any of the groups that he made. Or, what about fluorine? Fluorine fits pretty well here, but he didn't include it because he had these triads. So, that was the main problem, is that not everything fit into his triads. So we had to think of another way to arrange our periodic table. And there were many, many people between W Reiner and Dmitry Mendeleev. Dmitry Mendeleev was Russian, and he made his periodic table in 1869, so about 40 years after W Reiner. Again, there were many people in between, but Dmitry Mendeleev is considered the father of the periodic table. And if you look at the periodic table, there is an element 101, that is MD, and it's named after Dmitry Mendeleev, because, again, he is the father of the periodic table. He was the first person to make a periodic table that looks similar to the periodic table we have currently. Well, Dmitry Mendeleev decided that he is going to arrange the elements based on their atomic mass. So he put them in order of atomic mass. Let's write that down. Now, that itself is not really a great accomplishment. What is so amazing about Mendeleev is that when he arranged them that way, what he did was he actually took little cards, like you guys did, and he wrote the properties and the names of the elements, and he tried to, like, put them in some order, and so he picked atomic mass. But the brilliant thing about him is that when he did that, he noticed that there were periodic repetitions of properties. So he noticed that when he did that, he saw that lithium and sodium and potassium were all under each other, and they all have similar properties. And he noticed that with a lot of other groups as well. And the brilliant thing about Mendeleev is because he noticed these repeating properties, he realized that there were elements that have yet to be discovered, and he actually left empty spaces for those elements that were not discovered. He knew that we're missing some, and he predicted what those properties would be. And later on, years and years later, when those elements were discovered, they actually did have those properties that he did predict. So let's write all that down. So he noticed periodic repetitions of properties and left empty spaces for elements that were not discovered yet. So if you take a look at a periodic table here, first of all, element 101 is right here, named after Mendeleevium, or after Mendeleev, it's named Mendeleevium. It's an inner transition metal right here. But let's take a look at the periodic table. So for example, I believe germanium was not discovered by Mendeleev's time, but he realized that arsenic, for example, did not fit here. It did not have properties like carbon and silicon. So he said, nope, I'm not going to put it there. I'm going to leave an empty space. And then he predicted what properties germanium would have, what mass, what reactivity, and so on. And then later on, when they discovered it, it really did have those properties. So that was pretty brilliant and amazing. And that's why he is considered the father of periodic table, because the whole point of the arrangement of this periodic table is that, again, when you look at two elements on the periodic table, you can compare between them. You can say, this one is more reactive, or this one has a bigger radius, or this one has a lower ionization energy, and so on. So you can just look at the periodic table and be able to tell all these properties and compare between elements just based on where they are on the periodic table. Now, there were a couple of problems with his periodic table. For example, and this happened in a couple of places, but let's take a look at tellurium and iodine. So remember, he placed them based on their increasing atomic masses. So tellurium's atomic mass is 127.6 AMUs. Iodine is 126.90 AMUs. So according to the way that he should have arranged it, he should have put iodine and tellurium switched. He should have put iodine here and tellurium there, because iodine has a lower molar mass, atomic mass, than tellurium. However, again, the brilliance of Mendeleev is that he noticed these periodic trends of properties. And so he said, well, that doesn't make sense, because iodine fits really well with the halogens, and tellurium fits really well with the oxygen family. So what he did was he actually said, well, maybe we calculated the masses wrong. And he actually put iodine in its correct place and tellurium in its correct place. And, that was just an anomaly. That was a problem that he couldn't figure out what the problem was. And again, he just said, well, maybe we just calculated it wrong. Well, it turns out they were calculated correctly, but the current periodic table is not based on atomic masses. It is actually based on what? It is based on number of protons, on atomic number. And most of the time, with increasing atomic number, you get increasing atomic mass. And so that's why with Mendeleev, most of the elements fit in okay. But, you know, every now and then you did get that discrepancy that Mendeleev noticed. So Henry Moseley was the person who actually came up with the idea of arranging them based on atomic number and not atomic mass. So let's write that down. So Moseley was English, and I don't have the exact date, but it was in the early 1900s. He died in 1915, and so his work, I believe this was published in 1914, but I'm not 100% sure, but it was early in the 1900s. So he arranged the elements based on atomic number. And this was, you know, a really big step to producing our current periodic table. And this fixed all of the problems that Mendeleev had. So it fixed all of Mendeleev's, let's say, anomalies that he had seen on the periodic table. All right, the last person we're going to talk about is Glenn Seaborg. And Glenn Seaborg was American, and his work was in the 1940s. I believe he won the Nobel Prize in 1951. So we'll just say 1940s here. And his biggust contribution to the periodic table is he actually contributed by adding the lanthanides and the actinides, the inner transition metals. So there were a few of them discovered by the time of Moseley and Mendeleev. There weren't that many, and so they were kind of like scattered into the periodic table. He was the one who found a lot of other ones, and he, calculated their masses and stuff like that, and he then decided to place them at the bottom of the periodic table. So if you look at the current periodic table, having the actinide series and the lanthanide series right at the bottom here instead of, being in the middle of the periodic table, he was the one who did that. So that was a major contribution as well. Again, many scientists had worked and are still working on the periodic table. You saw that just in the last year or two, they discovered all these elements here, and so our 7th period is complete. They still continue work on our current periodic table. But these are the 4 main scientists that made huge contributions. So, periodic law says that if you were to arrange the elements in order of increasing atomic number, like they are on the periodic table, you do see periodic repetitions of their properties. That's what Mendeleev saw. And that is why it's called the periodic table, because you see the periodic repetition of the properties. So let's write that down. When elements are arranged in increasing order of atomic number, there are periodic repetitions of their physical and chemical properties. Which again is what's so great about our periodic table. Just to review on the periodic table, there are periods or groups, periods which are horizontal. So we say, since they're horizontal, they go across, so we say across a period. So when we look at these trends, we're going to see how they increase or decrease as you go across a period, and then also down a group or family. So the families are vertical and the periods are horizontal. So across a period and down a group or family. And remember that the elements that have similar properties, those are the ones that are in the same family or the same group. So we already talked about some of the families on the periodic table. This was back in chapter 2. So you are still responsible for knowing what family each element belongs to, and a little bit about their properties. And so you can just use your packet from chapter 2 to study for this test, or you can color these again. So there's room for you to color all the families and then also to write the notes. So again, pages 2 and 3 are just straight from chapter 2. So you can use your chapter 2 packet, or you can actually copy them. I think if you copy them, that will refresh your memory, and then you don't have to spend time studying, but it is up to you. Those are your notes. The one thing we'll point out is the representative elements. And so the representative elements are groups 1 and 2, and then also 13 through 18. So if you look at the periodic table, the representative elements are those 2 groups and then these 6 groups. So basically the S and P blocks. The reason why we call them representative elements is because they represent the elements on the periodic table when it comes to these trends in the properties. So when we look at, atomic size or reactivity or anything like that, when we say down a group or across a period, we are mainly talking about these representative elements. When it comes to the transition and the intertransition metals, because there are so many differences and exceptions in their electron configurations, the electron configurations are really the reason why we see these trends. And so because there are so many exceptions in these, those trends don't hold always true in the transition and the intertransition metals, but they do hold true definitely in the S and the P block. So that's why we call them representative elements. So now let's flip to page 4 and start looking at these periodic trends. You'll see that I left a space here for you to write what the periodic law is again. So that is something that is important. So again, this is saying that if you place the elements in order of increased atomic number, you will see periodic repetitions in their physical and chemical properties. That's what the periodic law is. So the reason why we see all these trends and repetitions in the properties is because of the electron configurations. So we are going to go ahead and write the valence electron configuration for these representative elements. Notice I didn't put the transition metals there because, again, we have a lot of exceptions there. So we're only going to do the valence electron configuration, meaning the electron configuration of just the outer shell. So let's go ahead and start doing that real quick. So this is 1s1, 2s1, 3s1, 4s1, 2s2, 3s2, 4s2, And then this is 2s2, 2p1, 3s2, 3p1, 4s2, 4p1, 2s2, 2p2, 3s2, 3p2, 4s2, 4p2. Nitrogen is 2s2, 2p3, 3s2, 3p3, 4s2, 4p3. Oxygen is 2s2, 2p4, 3s2, 3p4, 4s2, 4p4. Next are 2s2, 2p5, 3s2, 3p5, 4s2, 4p5. And then neon is 2s2, 2p6. Argon is 3s2, 3p6. And krypton is 3s2, 4s2, 4p6. So what do we see in the electron configurations as we go across a period and down a group? So it looks like if we go down a group, it is the same valence electron configuration, just a different energy level. So you see 1s1, 2s1, 3s1, 4s1. Or for example here, 2s2, 2p4, 3s2, 3p4, 4s2, 4p4. So again, same valence electron configuration, just a different energy level. So let's write that down. Same valence electron configuration, just different energy level. I'm going to use N for energy level. You can write out energy level, or you can just write N. Use your own abbreviations on your notes. Just make sure you understand them. So if I use N, and you know that when you look back in a couple of days to study for your test and you're not going to know what N is, then write energy level. So make your notes your own. Let's look at as you go across a period. So let's look at second period, 2s1, 2s2, 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, and so on. So it looks like we're in the same energy level, but we are adding one electron at a time to the same energy level. So one electron added at a time to same valence energy level. Again, I'm going to use N. You can write energy level, or you can write N. Now, we already knew that from the last chapter, but this is pretty important because of the way the valence electron configurations are, that determines a lot of other trends. So let's take a look at the next page. So the next page is oxidation number. Let's first define what oxidation number is. So the oxidation number is basically the charge. So it is the charge an atom acquires when it becomes an ion. And we already talked about that a little bit in the last chapter, but let's look now to see where is that coming from. And again, it's coming from these electron configurations. And so we're going to start with valence electrons first. So I'm going to go real quick back here and look at the electron configuration. So See how all of these end up with S1? So that tells us that it only has one valence electron. I'm going to go ahead and write that up here. The second group, see how they all end with S2s, and so these have 2 valence electrons. The next group, skipping the transition metals, let's look at group 13, 2s2, 2p1, so s2 and p1, that's 3 valence electrons. Next group, s2p2, so 4 valence electrons. Next group is s2p3, so 5 valence electrons. Next is s2p4, so that's a total of 6 valence electrons. And next is s2p5, so 7 valence electrons. And then we said these are s2p6, so 8 valence electrons. This one is just 2 valence electrons because it's just one s2. So if you look at the next page, I'm going to go ahead and write my valence electrons again here. So I'll write the valence electrons in blue. Okay, so again, we came up with this from our electron configurations because since it's the same valence electron configuration, those all have the same valence electrons, same with any of the groups. As you go across a period, because your electron configuration, you're adding 1 electron to the same valence shell, that's why your valence electrons are increasing as you go across 1, 2, 3, 4, 5, 6, 7, 8. Now, the elements, in order to be stable, they need an electron configuration similar to a noble gas. So they need to have the same electron configuration as a noble gas. So because of that, if you have 1 valence electron, if you lose 1, like if you're lithium, if you lose that 1 valence electron, you become like helium. Sodium, if you lose that 1 electron, you become like neon, and so on. So those lose 1 electron. Electrons are negative. If you lose a negative, you become a positive 1. So I'll do red for my oxidation number, which is the charge. These are all +1. Next, let's look at group 2. Group 2 has 2 valence electrons. So let's look at magnesium, for example. It could either lose 2, 1, 2 to become like neon, or it can gain 6 to become like argon. Well, it's much easier to lose 2 than it is to gain 6. So you lose 2 electrons. So if you lose 2 positive, or if you lose 2 electrons, you become +2 because electrons are negative. Skip to transition metals. Let's go to the boron family. They have 3 valence electrons. So for boron to become like a noble gas, it can either lose 1, 2, 3, or it can gain 5. So if it loses 3, it becomes like helium. If it gains 5, it becomes like neon. It's easier to lose 3 than it is to gain 5. So that's why they're +3. Let's look at the carbon family. The carbon family has 4 valence electrons. So if you have 4 valence electrons, carbon could either lose those 4 to become like helium or gain 4 to become like neon. It's just as easy to lose 4 as it is to gain 4, and so that's why we say these are plus or minus 4. Next group is the nitrogen family. They have 5 valence electrons. So for nitrogen, it can either lose those 5 to become like helium or gain 3 to become like neon. Well, now it's easier to gain 3 than it is to lose 5. 3 is less. So if it gains 3 and electrons are negative and they gain 3 electrons, then it becomes -3. Oxygen family has 6 valence electrons, so they can lose 6 to become like helium or gain 2 to become like neon. It's easier to gain 2. You gain 2 negatives because electrons are negative, so it becomes -2. The halogen family, they have 7 valence electrons. So much easier to gain 1 to become like neon than it is to lose all 7 to become like helium. So they gain 1 electron. Electrons are negative, so they become -1. The noble gases already have a noble gas configuration. Their S's and their P's are filled. They are stable, so they usually do not get a charge. They are very hard to bond and react, but when they do react, they do not gain or lose electrons. They don't get a charge. If they react, they'll share electrons. All right, so let's define oxidation number again, even though you have it up there. It's not going to hurt. So the charge an atom acquires when it becomes an ion, and it becomes an ion by gaining or losing electrons. And let's look at the trend across and down. So let's start with down. So if you look at a family, let's look at the first family. These are all +1s. So in a family, the oxidation number is the same. What is the reason for that? Well, the reason for that is because they have one valence electron. And why do they all have one valence electron? Because they have the same valence electron configuration, just a different energy level. So let's write that down. So the trend in the oxidation number as you go down is that it's the same. The reason is because same valence electrons, because they have the same valence electron configuration, just different energy levels. So how can I ask you questions about this? On the test, I could give you an element and ask you what is the oxidation number of it. Or I could ask you, hey, what's the trend as you go down a group? Or I could ask you, why is it that as you go down a group, it's the same oxidation number? So you need to know the explanation as well as what the trend is. As we go across, let's take a look. So, let's take a look at the second period, for example. So you go +1, +2, +3, +4, -4, -3, -2, -1, and 0. So that's our trend. As you go across any period, that is the trend. So let's write down the trend and then talk about why. So the trend is that it goes from +1 to +2, +3, plus or -4, -3, -2, -1, and 0. The reason is because you increase the valence electrons by 1 at a time as you go across. And the reason for that is because extra valence electrons added to the same valence energy level in the electron configuration. So again, I could ask you what is the oxidation number, I could ask you for what the trend is, or I could ask you for the reason for that trend. All right, this concludes our notes for today. I hope you have a wonderful rest of your day.